Problem 26, we're going to take a finite group and show that for any element, we can always find a power to that element that gets us back to the identity. So here's a reminder of what our groups look like, and this is what a to the n is, right? It's just a times itself a bunch of times, specifically n times. So how are we going to do this? Well, we want to take an element of the group, arbitrary, and find a power such that it equals e. So let's just start listing the powers here, right? So a squared is a times a to the third is a squared times a. And what we notice is we can just keep doing this forever, right? But the group itself, we're going to say that the number of elements in G is going to be equal to m. And so I don't know what m is, but I know that this process here that I'm doing on the right, I can do it forever. So as long as m is less than infinity, I can do it, let's call it L times. And what I've done is I've created a list of elements that exceeds the number of elements in the group, right? So I'm taking this L greater than m. And again, I don't know what L is, I don't know what m is, but I know that I can create this list such that this list over here has more elements than the number m. And when I do that, what we notice is, one, everything circled in blue is a member of the group because we have our closure axiom of the group, right? Two elements of the group multiplied together always yield an extra element. And so if everything's in the group, two of these elements have to be equal to each other because I have too many elements here on the right compared to the total number of folks in the group. So two of them are the same. And how I represent that down here is just a to the j equals a to the k. Again, I don't know what j and k are, but I do know that they're different, right? So like an example of this could be like a squared equals a to the fifth, right? I don't know what that j equals 2 and k equals 5, but that's an example here. I'm not saying a squared equals a squared, which is certainly true, but more importantly for us, we found two distinct integers such that this equation down here is true. And then what we can do is just manipulate it with the rules that we've been practicing in prior problems to find some power such that a to the j minus k equals e. Again, I don't know what j and k are, but I can assume that j is greater than k. Otherwise, you can just do this in the reverse order. So we just factored out an a to the k, and we found that that is our exponent that makes this true. Thanks for watching this video. I hope you enjoyed it. Make sure to subscribe so you don't miss out on future videos. And if you have a question about this problem or if you'd like to request a solution to a different problem you're working on, let me know in a comment below.